Okay, let's begin. So, first order of business, just want to get through some of the examples that we wrote down last time, just actually write out some cool solutions to a couple of them. Then try to tell you some things I should have told you a long time ago, but we've actually been using, just to be responsible. I believe we did one of them. We did the x sine x squared, right? I think we did that. Let's do that one. Okay, so what do you think?
U should be x cubed plus 1.
So we differentiate through x squared dx. We solve for the dx. And now we plug everyone in. 2x squared didn't do anything. That guy replaced with u, and our dx is du over 3x squared. X squares cancel, 2/3 comes out, and I'm left with the square root of u. So that becomes u to the 3/2 times 2/3. And that's it. About this one? How'd you do that one?
U is going to be cosine x.
Well, you could be cosine. U would be what? No.
No, negative sign.
The root of cosine is minus sine. Solve for dx. Now we plug in. Our cosine is u. We left the sine alone. Our dx is minus du over sine x. Those cancel. So I want to integrate just minus u cubed. This is minus u to the 4th over 4 with the power rule. And so that is minus cosine to the 4th x over 4 plus c. What was our substitution here?
U should be 1 plus square root of x.
U equals 1 plus the square root of x. Our du, d1 over 2 radical x. Solve for our dx. We'll get 2 radical x du. Go here and we plug it in. We have 1 over, well, there's a u squared, there's a radical x that we didn't do anything with, and our dx is 2 radical x du. Radical x cancels. Factor out the 2. This is u to the minus 2 du. That one. Yeah, so after a while, you really should get the hang of these. It's not going to be so bad. At first, it's going to probably take a while for you to recognize who the u is, but once you know how to pick the proper u, it's kind of follow your nose from there. Well, if you know the rules very well. Here's one that's quite nice. So here's an example of a definite integral, which I'll probably want to mention a couple things about that one. A couple ways you can look at that one. Okay, so what do we do here?
You can set u equals 3 plus x squared.
Could do u cubed equals 3 plus x squared, just to make it nicer, but whatever, this is fine. 2x dx, solve for the dx. And you go in and we plug everyone in. So x over the cube root of u, and our dx is du over 2x. X would cancel. How do we do that?
That's just like u to the minus 1/3, so it's just u to the 2/3 divided by 2/3 or times 3 halves.
U to the 2/3 times 3 halves times 1/2. That's 3 over 4 times our u was 3 plus x squared. I want to show you a couple ways to do this one. So last time I told you guys that u equals the natural log of x was the right substitution here. That's the nicest one, I think. One, we could do a little simplification. This radical x I can write as x to the half, and then using the log rules, I can bring that guy down. And so now, I'll say this way, du would be 1 over x dx, and so our dx would be x du. So this will be u, so 1/2, so x u, this will cancel. 1/2 du. Couple ways you can think about this. So method 1, it's basically to keep the old limits. In other words, you see these numbers over here, we know how to deal with that using the fundamental theorem of calculus. We actually did that a bunch of examples using that way. But notice here, these limits deal with the x coordinates. So when you do a substitution, you no longer have x's, and so the question might be, how do you deal with these limits? One way you can deal with these limits is to not do anything, keep the old ones. What you would do is you would actually indicate the variable, though. So you'd say here x equals 1 up to e. Right? So you realize we're working with the variable u, but I'm still thinking of my limits in terms of x. So you do want to have that reminder here. So you know you should not be plugging in these values into the u's. These are x values. So that's very important that you identify that. So what you can do is just continue as usual. So you'd integrate that, you get u squared over 2. So basically here we have u squared over 4. And this goes between x equals 1 up to e. Again, reminding myself that these are x values, not u values. But all I have to do now is just plug in, do the back substitution before plugging in those numbers. So my u was actually ln. And now I can plug in 1 and e according to the fundamental theorem of calculus. So I'll have ln of e squared over 4 minus ln of 1 squared over 4. Does this simplify? What's ln of e?
Just 1.
It's 1. You square that, you get 1, so you get 1 over 4. What's ln of 1?
0.
It's 0. So a quarter is your answer. Another way you could deal with this is that you can actually change the limits themselves. And so this is going to go back to what I mentioned last time, how you kind of never want to do the back substitution method if you're doing something like trig substitution, which you'll learn in Calc 2 towards the beginning. So here's method 2. You can actually change the limits themselves. And this is highly recommended for something like a trig sub or anything more complicated than a typical u substitution. As you'll see when you do trig sub, this idea to go from this step to that step, to go from the substitution variable to the original variable, when you're doing a trig substitution, that step is actually pretty complicated. There's a whole other set of calculations that has to happen between this step and that step. So it's probably wise, in any case where to get things back to the original way that they were understood, if that takes a lot of trouble, I'd rather you just change the limits. It'll be a lot easier. So here's what that would look like. So, okay, so let's pick up from here. So changing the limits. By the way, to do that, what you're going to do is you're going to use the substitution equation. So at some point here, we said u was ln of x. And so, pretty much what I'm going to do is I'm going to plug in x equals 1 and e into that equation. So I can say when x equals 1, this would mean your u is ln of 1 equals 0. And when x equals e, proceeding u is equal to ln of e equals 1. And so now I can start plugging in these guys and get to the 1/2 u du. The difference here is I can now put 0 and 1. And I don't have to state what variable that belongs to because it actually belongs to the variable u. Okay. So I'm not leaving the x limits, I change the limits based on my substitution equation. So I can just plug in whatever the x values are and solve for the corresponding u values. So it would be, I would get the same answer as if I were to just think of this as the original integral. And so here I would have u squared over 4 between 0 and 1. Plug in 1, you get 1/4. Plug in 0, you get 0. You get the answer back. So usually it's a matter of preference, but there are times when I would definitely recommend this way over just keeping the old limits. So normally, substitution, by the time you learn a lot more sophisticated methods, substitution is going to feel really easy. It's kind of something you can almost do in your sleep. So you just going through these extra steps isn't going to bother you, and you just might not feel like changing the limits, that's fine. But changing the limits has its advantages, especially if you're doing something like a trig setup. So you can leave the old limits or change the limits. If you leave them, a common mistake is to take these numbers and plug into the u's. You need to remember they actually correspond with the x's. So that's just another option there. Okay, what about this one? So I didn't tell you guys a substitution for this one. I wanted you guys to try and figure it out. So what's that one? Guys try here. Ideas? Just do these three and then we'll move on. Okay, let's do this because we need to do a little housekeeping after this. So, strangely enough, u equals the square root of x. What's the substitution? du would be 1 over 2 radical x. And so our dx would be 2 radical x u. So you plug that in. So we have 3 over notice here, radical x's would cancel. Still have an x here. So you might wonder, what am I going to do with that x? Well, you use radical x, which means that your x is just u squared. So this just becomes that. What's that guy? What do you differentiate to get 1 over 1 plus x squared? That's right, our tangent. So, that's the one there.
Why didn't you have to plug in at the last step on the first column, when you have 3 over radical x, 1 plus x, and then you plug in what we saw for dx, but you don't plug in u for the first radical x in the denominator?
Well, remember the goal, why we do this is because we want to eliminate the x variable and get something simpler, the u variable. The thing is, if I plugged in u here, what would that bad cancel with?
Yeah, no, I completely, that's because I tried this and that's where I got and I was confused, but
Yeah,
like,
so the trick was to not replace that right away. Is to actually leave the radical x to cancel with the first radical x.
so you can replace,
So I can replace.
you can replace one without replacing the other?
Yeah. We've done that before. Normally what we do is we replace the guy we substitute for u, and then we cancel the other guy, but that's just because coincidence. I mean, you can do whatever you have to actually get something in a nicer form. So I just left this guy here because I wanted to cancel it with that guy. That's why I left it. But then, of course, now I have to be able to rewrite this part, but then I just use my substitution equation. I get this one, which there were 2 inverse trig functions that we needed to know the derivatives of. That these were the inverse tangent and the inverse sine. So let me go to that. And this one also wasn't so bad. You apply a trig identity, it's a double angle formula. So sine of 2x. This is 2 sine x cosine x. And once I just plug that in, it becomes like one of the previous ones that we did. So I get cosine squared sine x. So u would be the cosine, du would be the minus sign, and so this guy would become minus 2 times the integral of u squared. So you get minus 2/3 u cubed, or you get minus 2/3 cosine cubed. Here we saw u equals arc tangent. Our du is 1 over 1 plus x squared dx. This means our dx is 1 plus x squared du. Plug that guy in. That will cancel that. So I just get the integral of e to the u, which is e to the u, or just becomes e to the arc tangent. For this guy was the double angle formula. This is 1/2 times 1 minus cosine of 2x dx. So this is 1/2 times the integral of 1 is x. The integral of this guy is going to be sine of 2x times 1/2. And where did that come from? Well, technically here, I did a substitution, u equals 2x, and ultimately I went up here. Which I guess that you can think of as a general rule. If you're looking at something like f of kx dx, you can realize that this is just 1 over k f of u du by doing a substitution. In fact, you can kind of do that with anything linear, in fact. So at some point, there are some things that, even though technically you would do them using substitution, they're kind of easy enough to do in your head. So once you have anything linear, a substitution is just going to divide by the slope. So if you have something like integral of cosine of 3x minus 4, well, it's just going to be 1/3 times the integral of that. You don't need to go through a substitution for that, because your u would be this guy, your du would be 3, you divide that 3 out, and that only works if it's linear though. A lot of students make the mistake of thinking, oh, they can always just divide by the derivative and that would be fine. No, you can only do that when it's a constant. Mention that because it is a tempting thing to do. So let me mention specifically that you cannot and you are not allowed to do this. If your substitution is not constant, you cannot actually do this maneuver. So I've seen students do things like, I ask them, what is the integral of e to the x squared? Now it turns out that has no antiderivative, we mentioned that before. But a lot of students would think that, oh, just take the derivative of the power and divide by it. Since the chain rule would say multiply by the derivative, can we just divide by the derivative? And And the answer is no, you cannot do that. Because once you throw another function in there, you're now in a product rule phase. So to differentiate this, you would need the product rule. It would actually split into two terms. You wouldn't get the original if you differentiated this. Right? But the idea is, if your substitution is just substituting a linear thing, the derivative would be a constant, so you can just kind of divide by the constant and just do the answer as if it were a single variable. So a little trick there, but do not use it unwisely. I think we've seen enough. You can finish off the rest. Let's just do a little bit of housekeeping here. It's things that we've been using, but it's long overdue that I actually specifically state them. Let's just make sure. Because they feel like just the natural thing to do, but you don't ever want to do something just because it feels like it's the right thing to do, because that can actually mess you up a lot in mathematics. You have to know that something is actually working. So at some point, we have to prove everything I'm about to write down, but you can just know that we have these properties. So long overdue. I just got into the mood of doing all these computations and I jumped the gun. So what I want to talk about now is some properties of integrals. So assume these functions, assume f and g are integrable, meaning we can actually find their integral, their antiderivative via Riemann sums or something, and the limit is actually going to work out. And assume that these guys are constants. C, little m, big M are constants. Here's one thing. If you integrate from a to b of c dx, you will always get c times b minus a. Now, you can just integrate this, you get c times x, you use the fundamental theorem of calculus, you plug in b and then you minus and plug in a and you get that. You can also realize that this is just asking you have a constant function at the level of c, and you want to find the area between a and b. It's actually going to be length times height, which is going to be this times that. And so you can actually prove that a couple ways. Two, something we actually use is that integrals distribute across sums. I didn't actually specifically state that yet. So if you want to do that, then it's just doing each individually. So this is something you can do in general. It wasn't particular to the examples I was doing. That's actually true. Integrals do distribute across sums. You can factor constants out. And an idea like that works for both the indefinite and the definite case. So you don't have to worry about either way. So A to B, A to B, B to B. 3, you can factor constants outside integrals. So if you have a constant times a function, this is the constant times the integral of the function. 4. Integrals maintain inequalities in the sense that if your f of x is greater than or equal to 0 all the time, then when you take its integral, you will get an answer that's greater than or equal to 0. In other words, if your function is always positive, it will have positive area underneath it. We mentioned last time about negative areas being a thing, as well as if you know that one function is greater than or equal to another function all the time, then the integral of this one will be greater than or equal to the integral of that one. if you can find a lower bound and upper bound for your function, okay, so let's say your function always outputs values that are actually greater than or equal to little m, smaller than or equal to big M, then it turns out that if you were to integrate from a to b of this function, it's obviously going to be less than or equal to, by this property, the integral of big M, which by property 1 tells us it's going to be big M times b minus a. And similarly, it's always greater than or equal to the integral of little m, which by property 1 will tell you it's little m times b minus a. So those are things that might come up. Those are some properties there. I do also want to specifically talk about the area idea. Is that refined language? We also thought of that as the area under the curve f, which I was put under in quotations. I want to specify that this means it's the net area under the curve. So it can be a subtraction and addition of areas. We saw this taking effect when last time we looked at the area under sine of x, I believe it was, between 0 and 2 pi. We got the answer was 0. And that was because it was computing the net area. It computed a negative part and it canceled out the positive part. And so that's kind of a better way to think of it, as the net area, and net being the key word here. So it's not a gross area, it's a net area. And so since this guy, the opposite of that would be true. This guy will return to you a negative value if your f of x is negative. So what I do want you to realize is that, so for example, if you have a function between a and b and it behaves kind of like this guy, and we can find the areas along here. So integrating from this guy to this guy will give you the area here. Integrating from this guy to this guy will give you the area here. And integrating from this guy to this guy will give you the area here. I want you to realize that the green parts will return to you a positive answer, whereas the red part will return to a negative answer. So if the area here is A1, area here is A2, and the area here is A3, and your problem was this is f. Then to find the area bounded by f, you would actually you would add these two, and then you'd actually subtract this. And so we'll probably do some examples of that next time. So this will actually give you a negative answer for the area if you actually compute the integral by our definition. So if you want to talk about the magnitude of the area being covered, you'd have to discover which part of your function dips below the x-axis, and you'll actually have to take its negative to make it positive. So if you want to look at the total bounded area as a magnitude, you have to be careful when your function dips under the x-axis, because this guy actually finds the net area. It'll actually give you a negative area in regions where your f is negative. So those are some important ideas. So the properties, we've kind of been using them without me actually telling you what they are because it kind of makes sense. I might have done some hand waving, but just want to write them down specifically, just to be responsible. Well, at this point I mentioned a silly example, I don't want to actually talk about that. What the heck, let's talk about it. Also recall, I did mention this before for sure, also recall. I did justify this using the fundamental theorem of calculus, so if you have like a to b of f of x dx, you could introduce convenient breaks into this guy like that. You can pick any number and you can, instead of going directly from a to b, you can put in a middleman whenever it's convenient for you. And so the example here, which I think I threw this in because I saw examples like this in your textbook. Suppose you know that the integral from 1 to 5 of f of x dx is 22. And you know that the integral from 1 to 3 of f of x dx 15, and you're asked to find the integral from 3 to 5. So sometimes you know about the error in certain locations, you want to figure out errors in other locations. You might want to do that for various reasons, which tomorrow's class I'll go a little bit into this. Applications of integration. We'll cover a lot more in Calc 2, but I'll just throw some out there. Why finding an area can be more important than just finding the area. In the same way with derivatives, why finding a slope can often be a lot more important than just finding the slope. There's all sorts of things we can do once we figure out how slopes actually work. We can do optimization, we can do related rates, we can do curve sketching, we can do a lot of things just by knowing about how slope works. So here, it's just to realize that the integral from 1 to 5, we can think of this as the integral from 1 to 3 plus the integral from 3 to 5. Sometimes they try to make this a little bit more confusing. But basically, you can just realize that you can talk about the function at different regions, talk about the areas at different regions, and you can kind of paste them together according to this kind of formula. And so that might help you figure out some unknowns. So knowing that this guy's 20 and knowing that that guy's 15, I can figure out what this guy is without actually knowing about the function itself. I can know about the area under the function. Well, of course here, subtract 15 from both sides, it's going to be 5. Yeah, just kind of want to mention those. I think we'll stop there. So tomorrow I'll talk about a few applications of integration beyond just finding area or how much space something takes up. And on Friday we'll probably do integration by parts. quiz tomorrow will be on stuff up to this point, I guess. Because it's kind of a continuation from last week. So know how to compute integrals, definite and indefinite, know how to do it with and without substitution. And that's kind of it. Tomorrow's quiz shouldn't be too bad.
That's the last one, right?
Come again?
That's the last one.
That's the last one, because next week you have your test in recitation.
When did we get that?